Hello, Stat 300, and this is Professor Gonzalez, and I'd like to do some problems from the assignment side of Alex. And this is homework set 11.2, and we're taking a look at the difference of two proportions. And so we actually have two proportions and doing hypothesis testing with that. This is section 11.2, and just to kind of show you a couple things, I made a document called test. Let me move back a little bit. This is the document called test number 4, formulas and tables. And these are very useful formulas for the test number 4 coming up. And chapter 9, hypothesis testing. Chapter 11, two sample hypothesis testing, which we're doing in this one, 11.2. Chapter 12, which we did some chi-squared statistics. And then also this little guy right here is really nice for when you're trying to find critical values right there. And we'll actually use that in this particular video. And then also the tables. So you've got your Z, positive Z scores or Z distribution. You've got your negative, you got your normal distribution, but your negative Z scores. Then you've got your T distribution, and we've talked about how that works. And then also from chapter 12, there's the chi-squared or the chi-squared distribution, and we showed how that works. So these are the different formula or tables, and then of course all the formulas right there that will be used. Let's get into this. Whoops, let's get on over to page number 1, if I can get there quickly. There we go, and I think I'll zoom back out. And what I'm going to do with this is I'm going to use color to help us identify the different, because there's going to be two proportions, right? So let's see, it says childhood obesity. A national health survey weighed a sample of 534 boys aged 6 to 11 and found that 80 of them were overweight. Now, before I continue, this book and this program, it does kind of a nice thing, and they define what proportion from the first population is. And right here it is, right here. I'm going to highlight that. Let P1 denote the proportion of boys who are overweight. Okay, so let P1 denote the proportion of boys who are overweight. So these are boys. Let's see. Yeah. Proportion of boys that are overweight. And let's use green. And let P sub 2 denote the proportion of girls who are overweight. Okay, so using color, I find it can be really helpful, at least when I'm teaching. So let's go back. And now we know what P1 and P2 are. And the book defined that for us, which is nice. Let's go back. A national health survey weighed a sample of 534 boys. So I'm going to go red there because they're boys. And found that 80 of them were overweight. They weighed a sample of green, 495 girls, age 6 to 11, and found out 69 of them were overweight. Okay, now here is a statement you need to highlight. Can you conclude that the proportion of boys who are overweight differs from the proportion of girls who are overweight? Now, if I go back and use my color again, can you conclude that the proportion of boys, so they're talking about boys. In fact, let me do this. Let me write boys here. And then let me write girls over here. And, oh, didn't we define boys as being P sub 1? And we define the girls as being P sub 2. So let's see if we could come up with a statement here that makes sense with this highlighted area. It says, can you conclude that the proportion of boys, I have this in red, whoops, what's going on there? That the proportion of boys who are overweight differs. Now, this is the number you need to key in on, because that's where they'll have language that would say greater than, like the proportion of boys who are overweight is greater than the proportion of girls. It might say less than, but this says differs. And when you see the word differs, you know that you're going to use this notation, not equal to. That's differs. So that defines what your alternate hypothesis is. So let me go down here and finish and do that part. So let's start with our null. H sub 0 is our null, and the null is always going to be P sub 1 equals P sub 2. You know, if you took a look at P sub 1 minus P sub 2, because you know how they're saying it's a difference of two proportions, and that equals 0, well, that would say, you know, if you have two things that you subtract and equal 0, that would say that those two things are equal. And so with our hypothesis test, we want that null hypothesis. We want to assume that they're equal. And then we're going to do tests and use statistics to see if our samples show that they're not equal and if they're, you know, going in one direction or the other. In this case, differs. So first of all, we're going to assume that they're equal, and then we're going to do statistics to see if we could reject that null and go with this new statement, this new idea that P1 differs or is not equal to P2. Now, you can, when you're looking at the hypothesis test, you got to figure out what kind of test to do. And it's always going to be determined by your alternate hypothesis, right? If it's not equal to or differs, it's going to be a two-tailed test like this one. If it is less than, it's going to be on the left side, left-tailed. If it's greater than, it's going to be on the right side, right-tailed. Okay, so let's move on here. So we've got the first two things or three things filled out. Let's get our information and use the proper notation. So here's our proper notation. First of all, it says that they're doing a sample of 534 boys. That means n sub 1 equals 534. And they're also saying out of those, they found out that 80 of them were overweight. Well, that's the category of the thing we're looking for. So x sub 1 is going to be 80. And this will allow us to get our sample proportion. Our sample proportion is going to be p hat from the first group, and it's going to be the total people sampled, 534, divided by the category or the thing we're looking for, and that happened to be overweight boys, so that's 80. And of course, if we divide that on a calculator, we get this to be approximately let me zoom in a little bit so I have more space to write, 0.1498. Okay, let's do the same thing for the girls over here. So we got the girls, we got the boys. So for the girls, we go and read through it, and it says they weighed a sample of 495 girls. So that means the n value, n sub 2, is 495. And they found out that 69 of them were overweight. So that's the thing we're looking for, overweight kids, or in this case, overweight girls. So it's 69. And now we want to get our sample proportion for this. That sample proportion would just be p hat from our second group. It's going to be out of 495, right? Wait, is that right? 495. And 69 of those girls were overweight. We grab the calculator, find out it's approximately 0.1394. Okay, so those are real important pieces to have there. By the way, there are some assumptions in order to use this test statistic that we're going to use. There are some assumptions that we're supposed to hold to, and here are those assumptions. I'm going to go ahead and look at them. They're down here. I'm looking at the bottom of the screen. And those assumptions are these guys. Let me see if I could kind of highlight them. I don't have a lot of space. Okay, here's the four assumptions. I'm going to use a little box. First of all, we have two independent simple random samples. Yes, they did say that they had simple, let's see, here they are, National Health Study weighed a sample. I think somewhere it said simple survey. Okay, so this was a simple random sample. Let's see, I didn't exactly say those words, but a national health survey weighed a sample of 534 boys aged and found out that 80 of them were overweight. They weighed a sample of girls. So this is justified as a simple random sample. And then we take number 2. Each population is at least 20 times as large as the sample drawn. Okay, well, the first population were the boys, right? And the sample drawn was, so let's do this. With the boys, the sample drawn was 534. And so the question is, if you multiply that by 20, that's what, 10,680. And so the question is, so here it is, each population is at least 20 times as large as the sample drawn from it. So each population is at least 20 times as large as the sample drawn from it. Okay, so the sample was 534, and multiplied by 20 is the national, it was a national sample. So in our nation, are there at least 10,000 boys? Yes, definitely, right? So that's satisfied. And also when you take a look at the girls, you'll notice a similar kind of thing. The girls happen to be 495. And is that sample that you're drawing from it at least 20 times bigger? If you multiply that sample by 20, we get 9,900-ish, right? Or 9,900. And there's definitely more than that in that population of girls in the nation. So that's checked off. So we're good there. The individuals, this is number 3. The individuals in each sample are divided into 2 categories. Yes, the individuals in each sample. So the sample of boys, what are the 2 categories? Well, it's the categories of overweight kids and not overweight kids. And then the other category of girls, or the other sample of girls, there were 2 categories there, which happen to be overweight girls and not overweight girls. So that was okay, that was good. Both samples contain at least 10 individuals in each category. Okay, so if we take a look at the boys, kind of zoom in so I have space here. You take a look at those boys there. I think we had what? P sub. We had the sample proportion. What was that? The sample proportion happened to be about 14%, so 0.149, a little more than 14%. And what was that sample size of the boys? Well, that was 534. And when you multiply that, that tells us there's about 80 people in that category. That was what category was that? That was the category of boys that were overweight. So there's about 80 of them that were overweight. And I think we can see that back at the original problem, right? Didn't it say the boys that there were 80 of them? There we go. 80 of them were overweight. So that category of the overweight boys is at least 10. Yes. It's greater than or equal to 10. So that's okay. And what was the other category? Well, you've got these are the overweight boys, and so the other category would be the boys that are not overweight. And you could multiply it by the complement, or you could just subtract 534 minus 80. Is that number bigger than 10? Yes. I'll just show you the math real quick, but you can do it multiple ways really, and you can just see that and verify it. But the complement of 14%-ish is about 0.8502. And when you multiply that by 534, we're getting about 454 boys that were not overweight, and that's definitely greater than at least 10 or greater than or equal to 10. Okay, and so you do the same thing with the girls, and you can see pretty quickly that the girls that were overweight at the beginning, it said were what, 69, so that's bigger than 10, and the girls that were not overweight, if this was out of a sample of 495, the girls are not overweight, that's definitely bigger than 10 as well. So number 4 is also satisfied. Okay, so this program or book doesn't really get in. They talk about it, but they don't really make you prove it or go through this really like I'm doing it. But I kind of wanted to do that at least one time to show you that those assumptions are supposed to be met before you actually run through this. Like I said, this program doesn't really make you do that. Okay, so I got that part at least addressed, I think. So now let's take a look at the next step. So remember what we did up here is we found HO and our alternate. So we've got our null statement and we've got our alternate, and then we've figured out what kind of test it is. It's a two-tailed test. So now let's go ahead and find the critical values. Now finding critical values is not too challenging because we'd have a handy dandy formula sheet that has a chart that'll help us a lot. So what you need to hone in on when you're trying to find critical values is you've got to look at the alpha. Let's go back and see what that alpha was. I think I'll use blue for the alpha. And I think we said, or purple, I think we said, where is it at? It says, why am I having a hard time seeing? There it is right there. It says use the alpha level of 0.01, level of significance, and the critical value method. And we've got two methods. We've got critical value method, or we've got p-values. Okay, so we're doing critical value method right here, and so that means that alpha is super important for us to use to find the critical value, and you're going to find out it's actually pretty easy. All I have to do is take that alpha level of 0.01, also realize that what kind of test is this? It is a two-tailed test. Those are two pieces I need to know. Alpha is 0.01, and it is a two-tailed test. Then I go down to my formula sheet. That's right there. You can see at the bottom of the formula sheet, it says that you could find critical values. Here are some common critical values with a commonly used significance level alpha. Well, we just said that the alpha level that we're looking for is 0.01. Here it is right here, 0.01. Then we also said we are doing a two-tailed test. So when you look at those two intersection points, there are our common critical values. That's the critical value for this problem. Plus or minus 2.576. They want us just to go to 2 decimals, so we'll go ahead and round that. So therefore, this is going to be plus or minus 2.58, since we're rounding to 2, since it says go to 2 decimal places. And the reason why you have 2 is because it's a two-tailed test. Okay? All right, let's take a look at the next piece. Now, the next piece is kind of where a lot of the work comes in. And it says, please compute the test statistic. The test statistic for the difference of two proportions, once again, is down here on our formula sheet. And it says the test statistic for the difference of between two proportions is this guy right here. Now, since you have two proportions, you also have to have a method of pooling those two groups together. And this is the easiest method right here, which is called the pool proportion method. But let's first start with looking at our formula. Well, it looks pretty impressive, that formula. I did copy it. And I put it right here for us to use. Let's see. Wait, where am I at? Wow, I did not get to the right place at all. Let's see. Did I put, oh, I did. I put the formula right here. So this is the formula just right off my formula sheet. And I'm going to put it right up here so we can take a peek at it while we're working. Need to make it a little bit smaller, I think. Okay, so we need to do that. Okay, let me zoom in so I have some space to operate. Nope, and I can't use that. Let me go back. So I'm going to have z equals. Now I need, I'm going to try to use some color to kind of highlight this, I think. I need to have my p hat right there for my first proportion. And I do have it. Remember that data that I lined up here? It is right here. So I'm going to copy that down. I'm going to copy that down right here. So this is 0.1498. The formula says to subtract. And then I need p hat from my second sample. So this is p hat is your sample proportion from my second sample. And when I look that up, there it is. It's from the girls. And that's 0.1394. All right. Now it says that I need to take my p hat, and this is pooled. So this is this piece right here. And how do we get that? Well, it's not too bad, but I think we better do the work right here. The way you get that is you take x sub 1 plus x sub 2. What was x sub 1? Well, it was those overweight boys. X sub 1 is 80, and x sub 2 is 69. Okay, so let's fill that in. X sub 1 was 80, and x sub 2 is 69. So that gets added together, and we're pooling together. Remember, these are two samples, and I need the pooled sample. And there's different ways of doing this. Is the easiest way, so I think that's nice to do something the easiest way, right? So n sub 1 is the sample size from the first sample. That's just 534. And the sample from the girls was 495. Now this is not typically how you add fractions because you're adding the numerator, adding denominator. It's you don't have to get common denominators because you're adding, and then dividing, right? So be careful how you put this in your calculator. When we add it up, we're going to get 149 over 1029, and then we put it in the calculator and we get approximately. And this is our p hat. Let's see, I'm running out of space quickly. Oh no, I'm not. So let's call this our p hat. And the p hat is approximately 0.14 when I divide it out 48. That p hat goes right here in the formula. So now that's what I have. I've got 0.1448. That gets multiplied by its complement. So you just take 0.1448. Sorry, you take 1 minus 1 minus 0.1448. And when you get that, it's just its complement. That's 0.8552. Now that gets multiplied by this little expression right here. So that little expression is just 1 over, so now we got the sample size from the boys. Which was what, 534. And the sample size from the girls, which is 495. And now this is two fractions, and you're just going to want to use your calculator, but you put it in a clear way, like I would put parentheses around those two and then add them up in your calculator, because otherwise you have to find a common denominator. You don't want to do that by hand. And when you add those two up, you get this decimal, which you're going to have to round, but 0.00389, and it keeps on going. Whoops. Now that gets multiplied by those three items, and don't forget, this is easy to forget, by the way, all that must be square rooted. Okay, let's see what we have. Up top, when I subtract those two, I get 0.14 0.0104. Down below, I'm going to multiply these three factors together, multiply them, and then take the square root. And when you do that, you get 0.0219478977. And that's going forever. Divide it on your calculator, and we're getting approximately 0.47. So 0.47 is our test statistic. So now you kind of know, you want to know what just happened here. So let's see. Let me zoom out a little bit. Okay, what just happened? Let me draw a picture. So remember we said that this was a two-tailed test. So let me show that. So there's our normal distribution. Right here is 0. And remember, that's our assumption, because remember, where can I write this? Remember our HO, or our null, said that P1 equals P2. So if P1 equals P2, if you subtract them, because remember this is the difference of two proportions, if you subtract them, you get 0. So we're assuming that the difference of two proportions is going to be 0. So 0 is what we're assuming to work. Now our alternate, remember, what was our alternate? I got to flip back to a page. Oh yeah, it was, I should know that. It was that they're not equal, that they're different. Okay, and so that caused us to do a two-tailed test. So we've got this two-tailed test thing going on. And we're doing critical values, right? Yeah. And remember the alpha level was 0.01. And two-tailed, what it does is it splits the alpha into both tails. So you don't really have to know what's in that alpha. It's not important with a critical value particularly. But I'm just kind of letting you know that that's half alpha there, and that's the other half over there with two-tailed. But what we do need to know is, we need to know what this critical level is. And what is this critical value? Because if we don't know what the critical value is, we don't know where to reject and not reject. Okay, so where do we get the critical value? Well, we got it from the chart. So we know that this is positive 2.58, and this is negative 2.58. Okay, so we know now that if our test statistic, what is the test statistic? Well, it comes from our sampling, and we sampled. Okay, so if it lands in this region to the left of our critical point, negative 2.58, we must reject. And if it lands to the right of 2.58, we must reject. And if it lands in between here, we do not reject. So I guess the philosophy here is that as we take samples, because we're trying to make the statement, if the weights differ, right? With this one, the weights, yeah. If the amount of overweight boys compared to the overweight girls, if it's the same or if it differs, and so we go out and sample, and just by chance, each time we do a sample, it's going to be a little bit different. Maybe do a sample is right on the money right there, but it's going to be by chance, not exactly what the population. So what this is the difference of the population proportions. And so we're assuming that they're the same. So the difference of two population proportions would be 0. We're assuming that. Now we go out and go to the population and sample it and plot that test statistic. And if it's anywhere in here, we're saying, well, by chance, it's going to be a little bit off, right? But if it's anywhere out in the red reject area, that is so far away from what we expect it to be. at that point we reject that P1 equals P2 sub 2 because it's statistically too far out for us to, well, we would say we reject it based on our alpha level of 0.01. Now let's see what happened. What in fact did we get? Well, we got a test statistic of 0.47, and 0.47, yeah, I mean that's like somewhere right here. So there's my test statistic at approximately 0.47, and that's definitely in of the region that we would expect it to be. So we do not reject, and when you do not reject, you really don't get a great strong statement. So let's see, determine whether to reject, do not reject. I mean, we can't even really say that HO is correct. We just know that we can't reject it, and we can't go with the claim that they differ. That was the claim. That was what we're trying to show, is that the weights, I probably should reread it. Well, actually, it'll come up here. So do not reject it. So remember, you only get great evidence when you reject the null. Well, do not reject the null doesn't give us a great strong outcome. The outcome is there is not enough evidence to make this conclusion. What was the conclusion we're trying to show? There's not enough evidence to conclude that the proportion of boys who are overweight differs. We didn't have enough information, or we did not have enough statistical evidence to show that it differs. Now, if our test statistic landed in one of these red regions on the left or right, at that point we would say statistically, we're going to reject the null that P sub 1 equals P sub 2, and we're going to go with the alternate, which is saying that they're different. And then down here we'd say there is enough information to say that there's a difference between those two. All right, but in this case we did not reject, and so there is not enough. All right, let's do the same exact test, different numbers. It's the same, not same test, but same scenario. And on this one, they want us to do the p-value test. Okay, so it's going to ask for, let's see, it probably says in the directions. So alpha level of 0.10 significance and the p-value method. Okay, so the critical value method, right? The critical value method was find your critical values. How do you find those critical values? You just looked them up on the table. If it was a right tail test, left tail test, two tail test, you looked it up on the table, plotted them. Then we had to figure out our test statistic using that formula that we just went through. You plot the test statistic. If it's in your reject area, you reject the null and go with the alternate hypothesis. If it's in the green, do not reject, then you can't say much. You can just say there's not enough information, or there is not enough evidence to show what you're trying to show. Okay, now p-value is a little bit different, because p-value is actually, stands for probability, but it actually is area under the curve. Whereas when you're doing critical values, of course you got alpha here, which is area under the curve, it's red, but you're really looking at these plotted points on this z, right? These are z numbers, and you're putting your critical values, and then you're seeing where the test statistic lands to reject or not. Now, p-values, you're actually looking at the area under the curve. Okay, let's do it. So we have a similar thing happening here, and I guess I'll go ahead and run through the same thing just to show you how I would do this. I start reading it, but I also know that they're going to say, well, let P sub 1, they're defining it for me, so I want to know what is that, so I can have my color. Oh, P sub 1 is a proportion of boys who are overweight. Okay, and then it says, oh, P sub 2, what's that? Well, that's the proportion, that denotes a proportion of girls. So these are girls who are overweight. So that allows me to start organizing. P sub 1 is the boys, and P sub 2 is defined as the girls. All right. What I also like to do is I like to figure out what my alternate hypothesis is. I know that every time p sub 1 equals p sub 2, that's our assumption. But, you know, the alternate might be a less than, greater than, or not equal to, differs, right? So let's see if you can identify where that's going to come from. And here it is. Can you conclude that the proportion of boys who are overweight is greater than the proportion of girls who are overweight? So can you conclude that the proportion of boys, right, that's P1, is who are overweight is, and there's the key word, is greater than. Can you conclude that the red is greater than what? The girls who are the green. Can you conclude that the red is, can you conclude that P sub 1, whoops, that's the wrong color. Can you conclude that P sub 1 is greater than P sub 2? So that's our alternate. We've got our assumption that they're equal, and we're trying to show that that P sub 1 is greater than P sub 2 by using statistics. Well, greater than, P sub 1 is greater than P sub 2. Well, that's going to be a right-tailed test. Whoops, tailed. And, you know, visually, if P sub 1 is greater than P sub 2, we're trying to see if it's, you know, how far it is to the right, and so that's why it's a right tail, okay? All right, now we need to organize our data here, and I'm just going to write down this stuff a little bit quicker this time because you saw how I did it last time. Turns out, oh, my sleeve is going to mess that up. So the sample size for the boys is nope, messing that up already. It is 535. We're interested in the overweight boys, and there happens to be 78 of them. P hat sub 1 is found by taking 78 divided by 535, and that gets approximately 0.1458. That's a pretty important number there. And then on the girls' side of things, sample size from that second sample, these are the girls, sample size was 529. The overweight girls, X sub 2, happened to be 62. And so our sample proportion from that second sample is going to be 62 over 529. And we put that in the calculator, and that's approximately 0.1172. Okay, so now we got our data all organized. And the next step, it says, okay, compute the test statistic. And once again, if you're not sure, you know, you could always go to your formula sheet. And there it is, test statistic for the difference between two proportions. So there it is right there. Okay? And also don't forget the pooled method of pooling those two samples for p hat. Okay, let's go back to where I was at, right there. Right there. And so I'm going to go ahead and start filling this out. So this test statistic is a z-score, and remember it's going to be p hat from the boys, which is about a little more than 14%, 0.1458, minus p hat from the girls, which is about 0.1172. Then we need to get our p hat from both, which is pooled. I'm going to write pooled. Remember the easiest way to do that, and this is how the book is doing it, and other books might do it in a slightly different way, but it is the overweight boys plus the overweight girls, and this is over the sample size of the boys, 535, plus the sample size of the girls, which is 529. And when we add that together, we get what, 140 over 1064, which is approximate. So p hat, this is not p hat sub 1 or 2, this is p hat, is approximately 0.1316. Okay, and let's see. Did you guys want to see that while I was doing it? Maybe I can move that over just so you're looking at it while I'm filling it out. Oh. So there's what I'm filling out right now. Put it up there. Oh, that doesn't work. Oh, it doesn't want to go there. Okay. Boy. Okay, so anyhow, so now you can see I need my p hat. The thing that I just found, I need my p hat. Whoops. I need my pool. Oh, my goodness, it's not working. Huh. Okay, so I can't write on that for some reason now. So I want that p hat. There we go. P hat. So I just got that. Here it is right here. So I'm going to write that down. That is 0.1316. Now it's times its complement. So 1 minus 0.1316 is 0.8684. And then you need to multiply that by 1 over n sub 1, sample size from the boys, which was 535. And then 1 over the sample size of the girls, which was 529. And you can calculate that on the calculator. And that gets multiplied. And don't forget, I'm going to put this in another color because people forget it all the time. Don't forget to square root that denominator before you divide it. So when you calculate that, up top you're going to get 0.0286. Down below, you're going to get, after you square root it, 0.02072. And this is a z-score, remember? So then I divide it and round it to 2 places. I'm going to get approximately 1.38. That is my test statistic, 1.38 approximately. Now I need to get a p-value. I'm going to get this thing out of here. It's now, the formula is in my way. Let's see if I can move it on out. Maybe we can move it out a little bit quicker by zooming out. Maybe. Maybe not. I think I had it parked right there. Okay, so let's move back in. Okay, so now what we want to do is we want to find the p-value. So I want to draw a little picture just to kind of try to highlight what that means. So we've got this normal distribution, right? We always have with the normal distribution 0. What we just found was our test statistic, right? Our test statistic is about here at 1.38. So remember how I said p-values is actually the area under the curve. So I want to, now remember this is a right-tailed test. So I'm trying to figure out, and actually I need to make that probably a little smaller to make it look better. Whoops. So I'm doing a right-tailed test, and my p-value is going to be the area to the right there, to the right of that z value. So remember, how do we do this? Well, you could use a calculator or you can go to a table. I'm going to go to a table. So I need to look up a z value. Now remember, z-scores on that table, it always gives you area to the left. So when I look it up, it's going to give me this stuff over here. And then I'm going to have to take 1 minus that answer to get my p-value, to get the blue on the right. So I'm going to go to my z table and look up positive 1.38. So I look up positive 1 point. Let's use some color here. There's 1 point. There's 0.8. So 1.38 is right there. So when I look that up, I get 0.9162. 0.9162. Let me go back to my work. So this area is 0.9162. So if I want the blue, I just take 1 minus 0.9162, and that will give me the p-value, which is 0.0838. I've got my p-value. Okay, determine whether to reject or not. So I'm going to get the full picture going here. So here's what's going on. Remember what our alpha is. Our alpha is 0.10, and we can find that right here. So our alpha, which is our level of significance, so of course this, as always, standard normal. So 10% of that, oh, it's pretty big, it's about there. So the alpha, it's a right-tailed test, so this alpha is 0.10. Now we just found the p-value, and it turns out that the p-value is a lot smaller, right? This is 0.10. Well, this is like 10 cents, and the p-value is like 8 cents. So if I looked at the area, if I superimposed that blue p-value, it's going to be like this, right? So the p-value is 0.0838. And remember, this is our rejection zone. I don't know if that's called rejection zone. Why did I do that? Anyways, rejection zone. If you're over there, you're going to reject. Remember, statistically, when you're looking at test statistic that comes from the sample, we don't expect it to be right on the money. We expect it to maybe be off a little bit by chance. But it turns out this is the level that we're not willing to call it by chance, is this rejection area, which is determined by that alpha 0.10. So in other words, this p-value is less than the alpha. Once again, that p-value is 0.0838, and that is less than the alpha, which, what was the alpha? 0.10. So when it's less than it, and you can see my picture, it's always, the further you go away from 0, the more you want to reject it. And if you get in that red zone, you have to reject it. So we must reject. So we reject the null. Let's kind of take a look at what that meant. Remember what our null was again? Our null said that p sub 1 equals p sub 2. It also said that our alternate said that p sub 1 is greater than p sub 2. And remember, p sub 1 were the boys. Remember, p sub 2 were the girls. So we rejected the null, and we're going to go with the alternate. So look at, there is enough information or evidence to conclude that the proportion of the boys, there's the boys, the proportion of the boys who are overweight is greater than, and there you go, you can see the language matching up with my notation, is greater than what? Is greater than the green girls, is greater than the proportion of girls who are overweight. Okay? So whenever whenever we reject the null, we actually are somewhat kind of happy because we're able to then make a stronger claim, and we're able to actually, can you conclude the proportion up here, the stuff in highlight, I'm able to conclude that now statistically based on an alpha level of 0.10. If you change the alpha level, it could change the answer possibly. Let's take a look at the next one. I would like to do this again. And we're going to do critical values again. This is just a different situation, but we're doing this, we're doing a critical value, then a p-value, then a critical value, p-value, just to get practice. Okay, so on this one, once again, this one actually, I think I'm just going to kind of go through it a little bit fast. This one is very similar to the other ones. Well, how fast do I go through it? I guess I better at least read it. In a random sample of 340 cars driven at low altitudes, 46 of them exceeded a standard of 10 grams of pollution or particulate pollution per gallon of fuel consumed. So it seems like there's a lot going on, and there's a dog barking in my house. But like I said, what I would do is I would go down here and see how they defined P sub the proportion from the population. They said let P sub 1 equal, let P sub 1 denote the low altitude vehicle exceeding the standard, and let P sub 2 denote the proportion of high altitude vehicles exceeding the standard. So what we can do here is we could say, okay, this is our low altitude, and we're going to call that P sub 1, and this is our high altitude vehicles. We'll call that P sub 2. And of course, we want to figure out what would they like us to try to conclude. There it is. Can you conclude, where'd it go? Can you conclude that the proportion of low altitude vehicles exceed the standard is less than the proportion of high altitude vehicles that exceed the standard? Boy, I'm ready to choke for some reason. So, low altitude vehicles we defined as P sub 1, and high altitude vehicles we defined as P sub 2. And here's the critical piece. Can you conclude that the red low altitude vehicles is less? There it is. There's the word I'm looking for, is less. Can you conclude that the red low is less than the green high altitude vehicles? So there is our alternate. That would be P sub 1 is less than P sub 2. And we also know that our assumption is going to be P sub 1 equals P sub 2. And since it's less than symbol, this is going to be a left-tailed test. Okay, and so now we go through all that. Now that we've got our color, we can, in a pretty easy fashion, go through and say, okay, there's 340 cars at low altitude, so N sub 1 equals 340. 46 of them exceeded, so that's X sub 1 equals 46. And then when we find P hat sub 1, that's just going to be 46 divided by 340. And when we do that, we get approximately 0.1353. And this guy over here, we go through and read for information. I'm an independent random sample of 85 cars. So we've got N sub 2 equals 85. Turns out 21 of them, so X sub 2, 21. P hat sub 2 equals 21 over 85. So our P hat sub 2 is approximately equal to 0.2471. Okay, so now find your critical values. Remember how you find your critical values? going to be very important that you, now once again, it's left-tailed, right? Okay, so I said correct. So it's left-tailed test. So essentially what I'm looking for, left-tailed test, I'm looking for that value right there. And an alpha level happened to be 0.10. Isn't that what they said? Alpha level. Alpha level of 0.10 or 0.10. And so what are the critical values? The critical value is going to be that point right there. And before I used red, I guess. So the critical value is going to tell me when I actually get into that rejection zone. So that critical value is important for us. You can use a Z table to go look it up because these are Z values. You can use that, and that's not too bad actually in this case. But we also have that faster way of doing it for looking for critical values. It's kind of made for it. And what we need to know is we need to know an alpha level of 10%, and it's a left-tailed test. So then we go to our formula sheet. We go to our formula sheet, and it says that it's an alpha level of 10%, or 0.10, and we said it's a left-tailed test. So there's our number. There's our critical value, negative 1.282. And I think they want 2 decimals, so negative 1.28. Okay, so we've got our critical value. Now we need to figure out the test statistic. And I went through that on the other problems, so I'm just going to go ahead and show you, well, let me show you one of the steps that I get to. The step before the end is going to be negative 0.1118 over 0.04392204. And when I divide that on the calculator, I get approximately negative 2.55. I've got to take care of a dog real fast. I'll be right back. There isn't a way of pausing this, unfortunately. I have to do a ton of editing. So there's that awkward silence. And I wish I could have edited that easier, but nope, we're going to keep on going here. So now we have our Z score. Now we want to determine whether we reject or not. So I'm going to draw that picture again. And you know, the more you do this, you probably don't have to draw a picture, but I think it's a good thing. So what we want to do is look at our normal distribution. There's our 0. We already found out that our critical value is to the left, it's negative 2.55. I'm sorry, that was our test statistic. What was our critical value? Critical value was negative 1.28. So, negative 1.28. Remember that negative 1.28 was determined. How did we get that? We looked it up, and it was determined because of this alpha level, right? So now if we end up, now that doesn't look very straight. Oops, wrong color. Now if we end up in the red region, we must reject. if we end up in this green region, we do not reject. Where do we end up? Our test statistic tells us where we land, and it turns out we did some sample data, and it turns out that that test statistic ends up at negative 2.55, which is definitely in this rejection area, somewhere to the left of negative, somewhere to the left of our critical value for sure. And so we are in the rejection area, so we must reject. So we must reject. Now, what did we reject? We rejected the null hypothesis. So let me kind of go back and let's kind of think about what that means. Remember, our null hypothesis said that our population proportion is equal to our population proportion for the first population is equal to the proportion of the second population. Let's say that a little better. But anyways, our alternate is saying that our proportion from the first population is less than the proportion from the second population. We just statistically showed that we must reject our null statement, which means we go with the alternate statement. Now, there is enough evidence, because we rejected, there is enough evidence to make the claim that P sub 1 is less than P sub 2. And so you're going to see that play out here in this statement. There is enough evidence to conclude that the proportion of low altitude vehicles, now remember, low altitude vehicles was P sub 1 and it was red. So I'm just going to use color to try to back that up. Conclude that the low altitude vehicles, exceeds the standard is less than, so there's our symbol right there, is less than what? The high altitude vehicles, which was P sub 2. Okay, and that's kind of how that works. Question number 4 of 4, this is our last one. This one has a little bit of a weird twist, so I wanted to talk about this one. And this one also goes back to looking for a p-value. So I just wanted to take a look at, the two options here really are critical value method or p-value method. But then you have some variations, left tail, right tail, two tail, okay? All right, let's go through this. The same question, but now it's p-value. So here's the sort of tricky part. We're going to start as we normally do. This problem is defining P sub 1 for us. So we'll go ahead and go with that. It says P sub 1, let P sub 1 denote the proportion of low altitude. Okay, so we're going to say P sub 1 is the low altitude cars, I guess is what we can say. Let's see, where did I go here? So P sub 1 is our low altitude vehicles that exceed the standard, and P sub 2 denotes the proportion of high altitude vehicles that exceeds the standard. Okay, now we want to see what kind of claim they're wanting us to see if we can make. Can you conclude, or a conclusion, I guess, can you conclude that the proportion of high altitude vehicles exceeding this standard is greater than the proportion of low altitude vehicles exceeding the standard? Now here's the mean little part. Let me read it again. Can you conclude that the high altitude, remember high altitude was the green, so they kind of flip-flopped the statement on us. All the other ones, P sub 1 was first and P sub 2 was second. But now they're saying, can you conclude that the high altitude vehicles exceed the standard is greater than, so there's that greater than, there's that important greater than symbol, is greater than the proportion of low, now remember low altitude vehicles were the red ones. And because we have our P sub 1 on the left, red on the left, and green on the right. But when we read it in our English statement, green on the left, red on the right, it kind of screws up our symbol a little bit. You got to be really careful. Can you conclude that the proportion of green high altitude vehicles is greater than? Can you conclude that the green is greater than the red? That's what it's saying. And that's the kind of nasty thing, is because I'm pretty sure that the computer is going to want you to put P sub 1 first. So P sub 1 is, of course, equal to P sub 2. That's our null. But then you're going to say P sub 1 is less than P sub 2 because of the unfortunate flipping of the high altitude and low altitude. So that can be a little bit tricky. P sub 1 is, now if you wrote it in reverse, it's actually, you could make it P sub 2 is greater than P sub 1. And that would be true, and I would be okay with that, actually. It's just that the computer is a little bit pickier, well, because it just doesn't know, I think. And if you run into something, and I keep on encouraging everybody, if you run into something, especially if it's a rounding difference of just minute differences, please email me, but you have to tell me the test number, and then I'll look it over, and in many cases, I'll award the points. So, but you have to highlight it for me. Okay, now, this is P sub 1 is less than P sub 2. It's less than, so this is a left-tailed test. Left-tailed test. Compute the test statistic. All right. So I guess I'll show all that again. I'm getting tired. Okay, so remember, we got to get our data. In a random sample of 335 cars at low altitudes, I'll use red. So that means n sub 1 equals 335 cars. 43 of them, so that means x sub 1 equals 43. So now I could get my sample proportion from the first sample, and that's just going to be 43 divided by 35, which is approximately something. It's approximately 0.1284. And then I get my data over here from the high altitude vehicles. It says an independent random sample of 88 cars of high altitude vehicles. So n sub 2 is 88 and x sub 2 is 21 of them exceeded. Now so my sample proportion from the second sample is going to be 21 out of 88. So what is that approximately? Well, that's approximately 0.2386. Okay, I needed all that to compute my test statistic. I also need to figure out the pooled sample proportion. So the sample proportion with these two populations, I got to pull them together. And so remember, these formulas are, I keep on highlighting this. Remember, the formulas are right here, and you can use them. This is what I'm working on right now, is trying to figure out my pooled proportion. And that pooled proportion is not too bad. All we have to do is take our 43 exceeding and 21 exceeding on the high altitude. So we've got our x sub 1, x sub 2, add that up top. Down below we have our sample size, or n sub 1, 335, and our n sub 2, which is 88. And add those guys up. And when we do that, we get 64 over 423, which is approximately 0.1513. That's our p hat, and that's important for us with our test statistic. So remember the formula for the test statistic. I like to say that. It's 0.1284 minus 0.2386 all over my pooled proportion, sample proportion, which was 0.1513, times its complement, 0.8487, times, remember, 1 over the sample size of the first sample, 335, and then 1 over the second sample, 88, sample size rather. You add those up, use a calculator for 8711. You multiply those three factors, and don't forget, so easy to forget, to square root that denominator. Up top, you're going to get a negative 0.1102. Down below, you're going to get after you square root it, 0.04. If this number is different, go back and square root it. You probably forgot. 0.042924. No, I misread that. Let me try that again. 0.04292427 9 ... Okay, divide that and we get our test statistic. Approximately negative 2.567. Says please round to 2 decimal places, so it's going to be approximately negative 2.57. That was funny how it did that. 2.57. Okay, so we have our test statistic. We do need, this method is the p-value method. So I think I want to draw a little picture. And let's see. I'm just thinking about what I can squeeze in here. So if I draw a little picture here, let me draw right here. We just found the test statistic, right? And that test, as a critical, if we were in the critical value side, we'd have to compare that, see where that test statistic lands. But on the p-value side, we want to basically convert this into the p-value, right? This is negative 2.57, and I want to see what area that represents, and that area is my p-value. So I can just look that up, right? I have a z-value of negative 2.57, and I can just go to my z-value tables, the negative one, and I could look up negative 2.5. That's right where? Right here. 7 is right here. And it comes together right there. 0.0051. So this p-value is 0.0051. So the question is, do we reject or not? And the nice thing about p-values is that they're always going to be positive, so you don't have to worry about a negative number being, being further away from 0. It's really, they're areas. So really what you want to do is you want to compare your p-value, which is an area, to your alpha, which is your area, which is your significance, level of significance. Well, this alpha, if we go back to the original problem, you can see the alpha is right there, which is 0.01. Ooh, that's a small alpha. Okay, So our alpha was 0.01. But our p-value is even smaller, 0.0051, right? This is not, if you're thinking about money, the red alpha is a cent and the p-value is like half a cent, right? It's, that would be, hundredths cent, and that's smaller than that. So it turns out that our p-value is less than the alpha. And when the p-value is less than the alpha, if you're into the picture, that means it means that the alpha was like this, right? It means the alpha was like that. And once again, if we think about that alpha as our rejection zone, we're definitely in the rejection zone. We are too far away from where P1 equals P2. P1 equals P2 at 0, and we are way too far. We set the limit at that alpha, and we are definitely in the rejection area. So we must reject the null. So we reject the null, and then now let's check out the statement. If you could reject the null, there is enough evidence. Okay, and the statement is gonna flip just like that original statement. I guess I'll talk about it. We're done, but remember what happened. P1, we assume that P1 equals P2. They're asking us to see if we can make a conclusion that P1 is less than P2. And if we use the language that they used, we got to change it around just like we did at the beginning. So this part's a little bit annoying, I think. Remember, P1 was the low altitude. The cars that had that low altitude emissions, and then P sub 2 was the high altitude. So if you look at the way they do the conclusions, just the same way they started the problem, there is enough evidence to conclude that the high altitude, see, so they start with a high altitude in the verbiage. So they're basically reading this backwards. That's what's happening. The high altitude vehicles exceed the standard is greater than the proportion of low altitude. Because if I read this backwards, yeah, the alligator is opening to the high altitude, if you want to go back to second grade. But anyways, the inequality is opening to the high altitude, so it's greater than. So it all makes sense. But boy, that one was a little bit tricky because they flip-flopped in their English statement there. Okay, I hope that helped. Hope everybody's doing great, and we'll talk to you soon.